There's a concept in physics that, well, it governs literally everything. I'm talking about why your coffee gets cold, why your room gets messy, and why the universe itself seems to have a one-way ticket through time. It's called entropy. And while it's often called the ultimate, unbreakable law, its final word might not be as bleak as you think. But let's start with something really personal. Why do we experience time in only one direction? Think about it. We remember the past, but we can't remember the future. We get older, we never get younger. Things fall apart, they don't just spontaneously reassemble themselves. So what's really going on here? Physicists have a cool name for this, the arrow of time. It's the reason an egg that splatters on the floor is never, ever going to uncrack and fly back into your hand. And what's really weird is that the deep, fundamental laws of physics, they don't care about time's direction. They work perfectly forwards or backwards. So something else has to be driving this one-way street we're all on. Okay, check this out. It's a classic demonstration from Bill Nye. He's got this container, right? It's filled with a total jumble of blue and white beads. He gives it a good shake. Now, you'd expect them to get even more mixed up, but instead, they separate, just like that, into perfect, ordered layers. Order seems to pop right out of chaos. So what gives? Did we just see time run in reverse? Did we just break a fundamental law of the universe? No, of course not. It's a really clever science trick. But this little illusion is the perfect way to start digging into what entropy really is, and maybe more importantly, what it isn't. Right, so that experiment gets to the heart of a huge misconception. Most of us, we learn in school that entropy is just a fancy word for disorder or chaos. But as we're about to see, that simple metaphor, it's not just incomplete, it's actually pretty misleading. All right, let's do a quick thought experiment. Picture two things. In one hand, you've got a cup of crushed ice. It looks all jumbled and messy, right? A structured solid. In the other hand, a simple glass of room temperature water. Now, if you're just going by the disorder definition, you'd probably point to the ice. But which one actually has the higher entropy? And the answer is the glass of water. And this is exactly where that whole disorder idea just falls apart. See, in the ice, those water molecules are locked into a rigid crystal structure. They can't move around much. But in the liquid water, even though it looks smooth and uniform, those molecules are zipping around, rotating, vibrating. There are just so many more ways for them to be arranged and for their energy to be spread out. To really get it, we have to stop thinking about chaos and start thinking about probability. And this brings us to the real heart of what entropy is all about. It's not some mysterious force pushing things toward decay. Nope. It's just a cosmic game of statistics. And in this game, the house always wins. Okay, to unlock this, we need two key terms. First, there's the macro state. That's the big picture view, what we see and measure, like the overall temperature or pressure of the air in a room. Then there's the micro state. This is the God mode view, knowing the exact position and speed of every single molecule at a single instant. So here's the absolute crucial takeaway. Entropy is just a way of counting the number of possible microstates that all look like the same macro state. A high entropy state, like air spread out evenly in your room, isn't something nature is trying to achieve. It just happens because there are an absolutely astronomical number of ways for the molecules to be arranged like that compared to any other setup. Think about the air in the room you're in right now. The macro state of all the air is in that one corner over there? Sure, it's possible. But there are very, very few specific arrangements, microstates, that would make that happen. But the macro state of the air is spread out everywhere? Well, there are a nearly infinite number of ways the molecules can be arranged to achieve that. The system just naturally wanders into the state with overwhelmingly more possibility. Just how unlikely is it? The odds of all the air in your room suddenly rushing into one corner are so mind-bogglingly small, you'd have to wait trillions upon trillions of times the age of the entire universe to even have a chance of seeing it. It's not forbidden by physics, it's just statistically impossible. Things break because there are a billion ways to be broken, and maybe only one way to be whole. It's just a numbers game. Okay, so this raises a massive question. If the entire universe is constantly just falling into the most probable, highest entropy state, then how in the world does something as complex, ordered, and wildly improbable as life even exist? How are we here? The key is to connect entropy with energy. A low-entropy system has useful, concentrated energy. Think of a battery or the fuel in a car. It's energy that can do work.
A high-entropy system has energy that's all spread out and dispersed, what we basically call waste heat. The energy's still there, but it's too disorganized to do anything useful.
So how does life pull off its magic trick? It brilliantly games the system. Life doesn't break the second law of thermodynamics, it exploits it. The sun is this giant cosmic furnace of low-entropy energy. It beams that useful, orderly energy down to Earth. And life, plants, animals, us, we capture that energy to build and maintain these incredible little pockets of order, our bodies. But in doing so, we radiate a whole lot of waste heat back out into space, increasing the total entropy of the universe. We're creating local order at the expense of creating even more universal disorder. Now, this process of constantly increasing the total entropy, well, it can't go on forever. So let's zoom all the way out. Let's ask what this unbreakable law means for the ultimate fate of, well, everything. This leads us to one of the biggest, most profound mysteries in all of physics. If high entropy, messy states are just so much more probable, why on earth did our universe begin in an incredibly special, highly ordered, and statistically impossible low entropy state at the Big Bang? The honest answer? We have no idea. Physicists actually call it the past hypothesis, which is really just a fancy way of saying, well, the arrow of time exists because the universe just started that way. But if we accept that bizarre starting point, the path forward seems pretty clear. From that initial, highly ordered state, the universe's total entropy has been going up, up, up ever since. The arrow of time we experience is literally just the universe moving from that ridiculously improbable beginning towards its most probable, inevitable end, a state of maximum entropy. And that final state has a pretty chilling name, heat death. Now, that doesn't mean it's going to be hot. It's actually the exact opposite. It describes a future maybe 10 to the power of 100 years from now, where the universe is in perfect balance. Everything is the same temperature, just a tiny fraction of a degree above absolute zero. All the stars have died. All energy is so perfectly spread out that no work can ever be done again. It's a cold, dark, silent, and final end to everything. Man, that is a depressing thought. The end of everything, forever. But is that really the end of the story? What if there's a fascinating, maybe even hopeful twist to this cosmic finale? Well, some physicists, like Sabine Hossenfelder, are pushing a really radical new perspective. She argues that what we call entropy isn't some fundamental, absolute property of the universe itself. It's a property that's defined by us, by the things we can measure, the information we have access to, and the kind of energy we find useful. Think about it like this. At any single moment, the entire universe is in one and only one exact microstate. It just is. The entropy isn't a property of the universe, it's a property of our description of the universe. We say entropy is high because we've lost track of the details. We can't follow every single particle, so we just average it all out into a blurry macrostate. Entropy goes up because we lose the information that makes one arrangement different from another. And this leads to a final, absolutely mind-bending idea. If entropy is really just a measure of what's useful and understandable to us, what does that mean for a universe in so-called heat death? Sure, to us, it looks like a useless, uniform wasteland. But could new, unimaginably different complex systems emerge that operate on rules we can't even conceive of? Could new forms of life arise for which that universe is actually a low-entropy, resource-rich environment? Maybe heat death isn't the end of everything, but just the end of things as we know them. And that is a pretty amazing thought to leave you with.